We're now going to see a problem with Monte Carlo estimation using a uniform distribution for P of x. So let's go back to the rendering image. So we're trying to render a scene with an area light and occluder that should cast a shadow on the ground plane. If we use a Monte Carlo estimator for the integral, when computing the irradiance at each point, and use a proposal distribution that is uniform over the hemisphere, then it will only very rarely hit the area light. This leads to high variance. In all other places where these rays do not hit the area light, the contribution to the integral will be 0. So there really was no point sampling there. This is essentially rejection sampling with a very wide distribution, with a uniform distribution over the upper hemisphere. And most of these samples are rejected. So there's 0 contribution to the integral. In order to be more efficient, we should find another solution. And that solution will be given by importance sampling. The math here is nothing different than what you had seen earlier. Here I just wrote down the equation for the Monte Carlo estimator, but we're highlighting the importance of this distribution P of x. So the function f of x is this complicated integrand, that complicated function we don't know how to analytically integrate. The problem with the previous slide is that we were sampling a lot from areas where the contribution to the integral was very low, or even 0. So instead, we're going to sample from a non-uniform distribution, P of x, that roughly approximates the integrand that we're able to sample from. And remember that sampling from this distribution required computing its integral to get access to the CDF and inverse CDF, which is why it has to be simpler than the actual integrand. So this P of x, our best guess for the integrand is big. It needs to be non-zero probability anywhere f of x can contribute to the integral. But we'll more heavily sample from these high contribution areas. And then the intuition for why we're downweighting the sample values by 1 over P of xi is that if we sample more heavily from some area, so an area where the density is high, then each contribution to the integral should be lower to keep it unbiased. Remember, we need to cancel out P of x. Now, if we sample very occasionally from the areas where the P of x is very small, we'll want to heavily upweight their samples in order to have an accurate estimate of the integral. That's given by this statement: if I sample x less frequently, each sample should count for more. In the lighting example, if we sample uniformly the solid angle over the hemisphere, so sample 100 random directions on the hemisphere, our rendering is super noisy. But if we instead use an importance sampling distribution that is uniform over the area of the light source, those 100 samples contribute a lot more, typically are contributing some amount of radiance to our integral. And that results in a much smoother image.